Okay, we're going to continue our discussion with average rate and speed and take another look at constant rate with lesson 11. All right, example 1 we're going to do in your journal. Pauline mows a lawn at a constant rate. Suppose she mows a 35 square foot lawn in 2.5 minutes. What area in square feet can she mow in 10 minutes or in t minutes? Solve this on your own before proceeding. So go ahead and try to figure this out before continuing the video. All right. What is Pauline's average rate in 2.5 minutes? Well, it is 35 divided by 2.5 square feet per minute. So what is Pauline's average rate in 10 minutes? Well, if we let A represent the area mowed, Pauline's average rate in 10 minutes is A divided by 10 square feet per minute. So since Pauline mows at a constant rate, C, then we know that 35 divided by 2.5 is equal to the constant rate, and we also know that A divided by 10 is equal to the constant rate. Therefore, 35 over 2.5 is equal to A over 10, which means A is going to be equal to 140. So Pauline mows 140 square feet of lawn in 10 minutes. If we let Y represent the number of square feet Pauline can mow in t minutes, then Pauline's average rate in t minutes is Y over t square feet per minute. Write the two-variable equation that represents the area of lawn Y Pauline can mow in t minutes. Well, if you take the rate from before, 35 over 2.5, is equal to Y over t, then we end up with the equation Y equals 35 over 2.5 t. So what is the meaning of 35 over 2.5 in the equation? Well, it represents the rate at which Pauline can mow a lawn. We can organize the information into a table. So if you were to copy this down, the linear equation Y equals 35 over 2.5 t, we can do a table that equates t time in minutes to Y, the area in square feet. On a coordinate plane, we will let the x-axis represent t in minutes and the y-axis represent the area mowed in the lawn in Y square feet. So then we have the following graph. Notice that for 0 minutes there's 0 feet mowed, and then it goes on up in a straight line from there. Because Pauline mows at a constant rate, we would expect the square feet of mowed lawn to continue to rise as the time in minutes increases. All right, let's take a look at our concept. So in the last lesson we learned about average speed and constant speed. Constant speed problems are just a special case of a larger variety of problems known as constant rate problems. Some of these problems, such as water pouring out of a faucet into a tub, painting a house, and mowing a lawn, were topics in grade 7. First, we define an average rate. Suppose V gallons of water flow from a faucet in a given time interval t in minutes. Then the average rate of water flow in the given time interval is V divided by t in gallons per minute. Then we define the constant rate. Suppose the average rate of water flow is the same constant C for any given time interval. Then we say that the water is flowing at a constant rate we're going to call capital C. Similarly, suppose A square feet of lawn is mowed in a given time interval t, which we'll call minutes. Then the average rate of lawn mowing in the given time interval is A over T square feet per minute. If we assume that the average rate of lawn mowing is the same constant C for any given time interval, then we say that the lawn is mowed at a constant rate of C. So describe the average rate of painting a house. Well, suppose A is square feet of the house is painted in a given time interval T minutes. Then the average rate of house painting is given in the time interval is A over T square feet per minute. Describe the constant rate of painting a house. Well, if we assume that the average rate of house painting is the same constant C over any given time interval, then we say that the wall is painted at a constant rate of C. So what is the difference between average rate and constant rate? Well, average rate is the rate in which something can be done over a specific time interval. Constant rate assumes that the average rate is the same over any time interval. As you can see, the way we define average rate and constant rate for a given situation is very similar. In each case, a transcription of the given information leads to an expression in two variables. All right, let's take a look at example 2. Water flows at a constant rate out of a faucet. Suppose the volume of water that comes out in 3 minutes is 10.5 gallons. How many gallons of water comes out of a faucet in T minutes? We'll write a linear equation that represents the volume of water, capital V, that comes out in T minutes. So let C represent the constant rate of water flow. So 10.5 divided by 3 equals C, and V divided by T equals C. Therefore, 10.5 over 3 is equal to V over T. Then, as you set up your proportion and solve it, we get the linear equation V equals 10.5 over 3 T. So what is the meaning of the number 10.5 over 3 in the equation? That number represents the rate at which water flows from the faucet. Using the linear equation, V equals 10.5 over 3T, complete the table. So your table should look like this. Every time you plug in a new minute, you get a new value for gallons. So on a coordinate plane, we will let the x-axis represent T in minutes and the y-axis represent the volume of water. Graph the data from the table. When you're done with that, compare it to this graph. Again, 0, 0 is one of the points on our graph because in 0 time we have 0 gallons. So from there it increases 1 to 3.5 gallons, and so on and so forth. So using the graph, about how many gallons of water do you think would flow after 1.5 minutes? Explain. So if we go back to the graph, we would find 1.5 minutes, and if we were to have a line drawn here, we would notice that it would cross that line about between 5 and 6. So after 1.5 minutes, between 3.5 and 7 gallons of water will flow. Since the water is flowing at a constant rate, we can expect the volume of water to rise between 1 and 2 minutes. The number of gallons that flows after 1.5 minutes then would have to be between the number of gallons that flows out after 1 minute and 2 minutes. So using the graph, about how long would it take for 15 gallons of water to flow out of the faucet? So let's go back to our graph. If we go up the y-axis to 15 and across to where this would meet, we notice that it would be greater than 4 minutes, but less than 5 minutes. So it's going to be somewhere between 4 and possibly 7 minutes. So using the graph, it would take between 4 and 5 minutes for 15 gallons of water to flow out of the faucet. It takes 4 minutes for 14 gallons to flow, therefore it must take more than 4 minutes for 15 gallons to come out. It must take less than 5 minutes because 3.5 gallons flow out every minute. Graphing proportional relationships like these last two constant rate problems provide us more information than simply solving an equation and calculating one value. The graph provides information that is not so obvious in an equation. So that's why it's good to graph equations so that you can get a visual as to how it might affect other values. All right, let's take a look at exercises 1 through 3. Complete those on your lesson worksheet and then check your answers by continuing the video. Here is the answer to 1, or the part answer. Again, make sure that you're paying attention to the way the problem is set up. Making a connection between constant rate and the average rate, and then solving for the equation. And then using that equation to get approximations, since these are going to be longer than 1 decimal. And it says to use your calculator, round your answers to the nearest tenths place. All right, the graph of this would look similar to this. And for part D, again making a verbal statement of comparing a graph, or using the graph to solve the answer. Okay, question 2, same method to come up with an equation. Applying that equation to a table. And then graphing that equation and using that graph to make an approximation about a certain value. Right, for part C, the same thing, or part 3 I should say. And here is the table and the graph. And last, part D. All right, let's wrap this up. Constant rate problems appear in a variety of contexts like painting a house, typing, walking, water flow, etc. We can express a constant rate as a two-variable equation representing proportional change. And we can graph the constant rate situation by completing a table to compute the data points. All right, we'll see you in class.